Hello everyone. Welcome to the second part of this discussion on animation. So in the first part we went over the worksheet, just kind of did some practice problems, and then now what we're going to do is actually write some code and get some hands-on experience for how animation is actually implemented. Okay, and we're going to do that through a rope simulation. So it's kind of a simplified version of the cloud simulation project. Okay, so let's get started with part one. So part one, linking the rope constraints. So in rope.cpp, implement the rope constructor. It should create a new rope object starting at start and ending at end, containing num nodes nodes. So it's something like the following diagram, where each of those O's or zeros is a node, and then the dashes are kind of the rope in between. The nodes at the indices specified by pinned node should have their pinned attribute set to true. Make sure to pass along the node mass constant into the mass constructor and k into the spring constructor. K is the spring constant. You should be creating a new mass object for each node in the rope and link together adjacent pairs of mass objects with spring objects. Okay, and then after we do this, we'll run rope sim, and we should see our rope drawn to the screen. Okay, so let's go ahead and get started. Okay, so I have my code editor. I'm going to go ahead and open up rope.cpp first of all. Okay, so here we go. There's a little bit of documentation to kind of help us out. So we want to create a node, create a rope. New masses can be created with this call and should be added to the masses vector. Springs can be created like this, should be added to the spring vector, and then masses corresponding to indices and pinned nodes should have their pinned field set to true. Okay, so before we do this, let's just kind of go through here real quick, the rope.ahc, what the class is about. So here are the masses and springs objects. Those are where we're going to add the masses and the springs. Here are the constructors and then two functions that we're going to implement later on. Let's also check out mass, so mass, pinned, start position, position, all of that good stuff. Same with spring, just to kind of know what we're working with, okay? So now that we've looked at everything, let's go ahead and get started. We'll follow along with the pseudocode and see where that takes us, okay? So the first thing we're going to do is calculate basically how far subsequent nodes should be from each other. So the way we're going to do that is find the distance between the beginning and the end, and then divide it by 1 minus the number of nodes. And then, now that we have this, we're going to go right. We want to add the number of nodes. Okay, so that's basically, we're just going to calculate the position of the ith node. So the first one's going to be start, then the last one will be end. Then let's go ahead and create the mass. So just follow the exact the syntax they gave us in the documentation right above. Then put the position in, which we just found. The mass was given to us as node mass. And then the bool, so if we come in here, I believe that's going to be pinned or not, right? So let's go ahead and just set that to false for now, and then we'll come back later and make sure that whatever should be pinned is pinned. Okay, and then we're going to go ahead and add that. So we're going to go here, this vector of mass pointers, and we're just going to go ahead and push that back in. Okay. Now what we want to do is we want to create springs to connect pairs of masses, right? So what we're going to do first of all is we're going to check whether I is greater than 0, right? Because and you'll see why we do this in just a second, but it involves our construction. So just like the mass, we use the same code they gave us. So now we're interested in the masses, right? The two masses we're connecting. And the way we're going to do this is we're going to go m, which is the one we just created, and we're also going to do masses at I minus 1. Okay, and what this is this is the last mass created, the one right before this, and this is why we have that if, checking if I is greater than 0, because if I is 0, then I minus 1 is -1, and there's no -1 spot in the vector, right? And then we pass in k, which we're given. So now we have this, and then we're just going to add this to our springs vector, right? And then, so there we go. That's a construction. You know, we've added the masses, added the springs, looking good. Now the last thing we have to do is make sure that the masses that should be pinned are pinned. And so the way we're going to do this is going to walk through this. Right, so iterate through all indices that should be pinned, and then we're just going to go masses at I, and remember this is a pointer, so we have to use this arrow notation and set it to true. Okay, so simple enough. You know, create masses, add them, check if it's greater, not the first one, and then create springs to connect them, and set the pinned equals to true. Okay, so if we check here, now that we've done this, if we run the executable, we should be able to see something. So let's go ahead and try that. Let's make it first. Okay, and rope sim. Okay, there we go. We have a rope. It's not doing anything, but we have a rope, so it's a great start. And let's keep going. Okay, so we're done with part one. What about part two? Explicit Euler. Okay, so Hooke's law states that the force on 2 points along the spring is proportional to the distance. So this equation looks really weird, but it's basically just, you know, F is equal to kx times this unit vector, which tells us basically the direction we want to go in, and x is the displacement. So in rope simulate Euler, first implement Hooke's law. Iterate over all springs and apply the correct spring force to the mass on either end of the spring. Ensure that the force is pointing in the correct direction. Accumulate all forces due to springs in the forces attribute of each mass. Once all of the spring forces have been computed, apply the laws of physics to each particle. And these laws of physics are essentially the forward Euler or explicit Euler simulation step, right? And we see these equations right there. Okay, and then we'll run it and see what it looks like. So let's go ahead and get started. So here we go. The simulate Euler function, this is where we're going to be writing all of our code. And so, okay, let's go ahead and get started. So it starts off, you know, we're going through this for loop of all springs, okay? So what we're going to do is find the length of the spring, SM2, okay, so that's just taking the two point masses on either side, subtracting the position to find how long this string is, this rope is, and then given that, now we can find the displacement. Okay, so now that we've calculated this, what we can do is actually find the force, right? And so this is where Hooke's law comes into play. So it's going to be the displacement times the k, which is the spring constant, times the unit vector of this difference, right? This diff is the vector from one side of the spring to the other. So that's also going to tell us kind of the direction that the force is applied for one of the masses, and it's going to be the opposite of the direction for the other mass. Okay, so now that we've done this, let's go ahead and actually add these forces to the mass. So M1. Okay, so now we have to think about how we want to apply this, right? So the diff, the vector 2 diff is going from, we subtracted S1, oh whoops, I realize now that I made a mistake there. That should be M1. Okay, we said M2 minus S1, right? And so that means that in this case, what's the best way to put this? But it's in the direction of M1, so what we're going to do is we're going to go add it to M1 and subtract it from M2. Okay, so we have to apply it in opposite directions. So we add it to one, subtract it from the other, because that's how, because you know the forces on each of the point masses point in opposite directions. Okay, so that's all it is for now. We calculate the force, apply the force to the point masses. Now we're going to come down here and actually code in the explicit Euler step to actually update the positions of these point masses using these equations right here. Okay, so let's go ahead and do that. So so first we're going to set the velocity. Right, so forces over mass is the acceleration, and then we're going to add gravity to that, right, because it tells us add the force due to gravity, and then compute these new values. And then delta t is the time between, how long between updates. And then now that we have the velocity, we're going to go ahead and update the position also. Okay, so there we go, we've updated the position. And then the very last thing that we want to do is prepare ourselves for the next round of simulation. And to do that, we're just going to reset the forces to a 0, 0, 2D vector. Okay, so up here we found the displacement, found the force, added, subtracted, then we completed the actual explicit Euler step, and then reset everything to get ready for the next round. Okay, so now that we've done this, we can go ahead and test it. So let's do that. Let's make it again, run it. Okay, so that shouldn't happen. Or, well, that should happen. So we see this blue rope, going kind of crazy. Right, so let's see. Change the 3 value to a higher constant like 16. Okay, I feel like it's already higher, but let's go ahead and take a look. Application.cpp. Oh, yeah, CPP. At the top of app. This is awkward. Where does this define? Oh, okay. So I think it's over here. Looks like they're already 16. So I'm just going to go ahead and skip that step. Sorry for the confusion. Okay. So now let's try this. It says run this to set a different number of simulation steps per frames. So the default is 64. So what we're looking at right now is 64, right? And so let's go ahead and try this again with 32. Okay, so it looks a little different. It seems to kind of take longer to diverge and go crazy, and that's mainly because we're doing less steps per frame, so there's less error accumulated per frame. Okay, okay, so that's kind of a basic explicit Euler implementation. It works okay, but we can kind of see some of the downsides of explicit Euler because we can see it go crazy, the error is accumulating, all that good stuff. So let's move on to part 3. So now we're going to do explicit Verlet integration. I believe that's how you say it. I might be wrong. So it's a different way of ensuring that all constraints are dealt with accurately. The benefit to this approach is that the simulation is handled entirely through the position of the vertices in the simulations, and it remains fourth order accurate. Unlike Euler, Verlet integration follows the following rule to calculate the position. Okay, so they give us a position. It's 2 times x of t minus xt minus 1 plus at times dt times dt. Okay, we also now emulate springs with an infinite spring constant. So instead of bothering with spring forces, you just move every mass so the springs are back to the rest length, and the correction vector should be proportional to the displacement between them, and each mass will move by half the displacement. Okay, and so as long as we do this right, our simulation should approach stability. Okay, so let's go ahead and do it. Right, best way to practice is to do it. So here we go. So we want to go through each of these strings and simulate one-time steps. So we're going to start off very similar to how we did the explicit Euler, right? Take the difference of the positions, find the displacement just like last time. Cool. Okay, now this is where it's going to be. So move each mass by half the displacement. So, but before we do this, we want to make sure that neither of these are pinned, because if it's pinned, then and we move it, then we might just, lose the whole rope from our vision. So okay. So remember, same as last time, we're going to add to M1, take away from M2 because of the direction our vector is pointing in. And so we're going to do diff.unit times 0.5, right? Because so diff.unit is going to give us the direction to move in, 0.5 because we want to move each mass by half the displacement, and then the actual displacement value, right? So that's all there, and then we're going to do the same thing, but for the other mass. Minus equals okay, so there we go. We've moved both masses by half the displacement. Okay, so that's all for this spring for loop. Now let's come over here to the masses. Right now that we've actually moved the masses, what we want to do is set the new position of the rope mass. Right, so we want to actually compute this. We have the point masses, now we want to do that step. And so the way we're going to do this is, let's come down here below the to-dos, and so m-position is plus equals, should it be plus equals? Okay, so there's two ways we could write this. So we could do 2 times m-position minus the last position, right? And so this is going to be last position plus gravity times delta t times delta t. Okay, so we're solving this part. Right, we've basically rewritten this equation, and yep, that's it. And then what we're going to want to do is set this last position to this temp position variable that we set, because we'll need it for the next time step. So we want to make sure we keep that updated. So let's put, okay. So this should be an implementation of the Verlet integration. So let's go ahead and run it. See if I wrote this right or I messed something up. Oh, okay, I'm missing a semicolon. Okay. Oh. Okay, so I accidentally ran it with 32. That's not a big deal, but so the green here is the rope with Verlet integration. The blue is with Euler. So as you can see, it's pretty obvious that the Verlet integration is doing much better than the Euler. Euler, has all sorts of errors, doesn't look very realistic at all, whereas the Verlet does look pretty good. Okay, and I'm just going to go ahead and run it once without the modified frame rate, just so you guys can see. Okay, so as you can see in this case, it's moving faster because we're taking more steps per frame. Okay, so we have a working explicit Euler, explicit Verlet. Now what do we do? So one thing you may have noticed when we were running it just now, and I can run it again just to see, is, well, they don't stop, right? Normal rope, if you let it go, it'll bounce for a little bit and then stop. This is just continuous. And the reason for that is that we're not actually applying any damping. So let's go ahead and do that, okay? That's the next part of this. So part 4, damping. So let's add some damping first to Hooke's law in explicit Euler. In a spring damper system, an additional damping force is applied. So you see, springs in real life don't continue bouncing forever. The damping force is proportional to the relative velocity of the two particles. Use a damping constant of 0.5. Okay, so let's go ahead and do this. If I come up here, here, right? And so the place we're going to want to do this is here. We're going to want to add a damping force to the point masses on either side of the spring, okay? And so before we do this, we need to get some kind of background information. So the relative velocity, we're going to do m2 velocity minus m1's velocity. And then we're going to calculate the actual damping force. And okay, damping constant of 0.5. So it's going to be 0.5 times this relative velocity. And then what we're going to do is, whoops, so let me take this and move them down here. And what we're going to do is we're basically just going to add the damping force here and subtract the damping force here. So kind of keeping it in line with what we've seen earlier, okay? And so let's see how this goes. Let's run it. And let's go. Okay, so as you can see, it damped, but it was damped super fast, like immediately, right? So that makes me think the damping constant is a little high, this 0.4. So let's turn it down, maybe 0.3. I feel like this may still be a little high, but we can play with it a little, right? So look, still pretty fast, kind of unrealistic. Let's go ahead and make it really, really small. Okay, so now there we see that blue rope. That looks much better, right? It slowly damps as we'd expect it to, kind of slowly comes to a stop flat. Okay, so there we go. We've added damping to this explicit Euler, but the Verlet integration is still just clicking away like a metronome, right? And I'm not sure why the spec says 0.5, but that's a little too much. So maybe 0.05 is a little better to get a more realistic feel to it. Okay, so now that we've done that, let's look at part 4.2, which unfortunately doesn't have a lot of instructions, but what we're going to do here is we're actually going to go ahead and apply this to the Verlet integration. So this is the same kind of damping effect, but for Verlet instead of Euler. So the way we're going to do that is turn this 2 times x to t into 2 minus damping factor times x to t. And so we're going to use a super small damping factor over here. Okay, so let's come down and try it. So what I'm going to do is I'm going to go 2 minus 0. What they suggest, 0.0005, 0.0005. Okay, super simple. Damping in this case, super simple. We just add this. Well, I say super simple. Hopefully it works. Let's try it. Whoa, 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 whoa. Okay, so I have no idea what's going on there. That's looking pretty weird. Let's see if we can figure out what to do about that. Let's see. Let's try a slightly larger damping factor. See if this helps us out. Nope, still crazy. Okay, so what I'm going to do actually, and this is a little bit of cheating, but that's okay, is I'm going to look at an older version of my code where I got this working. And I'm going to go from there. So sorry about this, everyone, but let's take a look at how. Okay, so it looks like okay, so I used a 1 instead and then did that. Okay, so let's try this. Let's try that. Nope, that totally disappeared. 1 minus, add a couple zeros. Let's try this. Whoa, 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 what am I even doing anymore? Let's keep that at 2 actually, because I realized I did it wrong. Okay, so I'm not sure what's going on here. Sorry about that, guys. But here's some code that does work, and I'm just going to go ahead and show it to you so you know what it looks like when I can do it properly. Let's go into build, make that cool, and rope sim. Okay, and there we go. So there's our green Verlet integration. It's looking much better now. There's, we can see the damping, but we can also still see how it's kind of not as error, not, it doesn't have as much error as the explicit Euler does, right? So it's kind of much more natural, much better feel to it. So there it is, and yeah, there we go. That's damping for the Verlet. I'm sorry I couldn't get it to work live. You all have to go back and look at why. But there we go. We've come up with a very basic rope simulation. You all will see a much more in-depth version of this in Project 4, where you do some cloth simulation. Okay, so that's all for this discussion. Thank you all for watching.